Well, thank you to the organizers. Thank you all for coming to the first talk in the morning. So I will talk a little bit more about what Anu talked about already, coding for interactive communication. Okay, so I will just, in the beginning, quickly go over the model again. And if at any point of time there are questions, just ask. You know, we can always cut off material in the end, doesn't matter. It's more important that everybody understands roughly what's going on. Okay? So coding for interactive communication is basically error correction for conversations. So I claim we know very well how to do error correction for one-way communication. So that's basically error correcting codes, right? So that's a classical setting. We have two parties, Alice and Bob. Alice has some information, let's say n symbols, n bits, and it wants to send it to Bob. Okay, well, Alice sends them to Bob. But now we have noise, right? So what if of the n symbols that Alice sends, some constant fraction of these symbols get corrupted? Any fraction, any delta, let's say, I don't know, 10%, 20% of these symbols get corrupted. Well, now Bob obviously doesn't know what Alice wanted to send him. So what can we do? Well, we just make the transmission a little bit longer, right? So what do we do? Instead of sending n symbols, Alice sends alpha times n symbols for some constant alpha. And now if you do this in the correct way, if you use error correcting codes, then no matter where these 10% of errors happen, Bob will always know exactly what the outcome in the noiseless setting was. Right? Turns out to be pretty useful. Now, most communications aren't just one way. Most communication, I tell you something, you respond, I respond to that. We want to find a research project, we want to find a lunch place, a time, date to meet. You know, most of these information go back and forth. So now we want to have such a conversation in a noisy room. Right? Well, what's the model? Basically, we have two parties, Alice and Bob, and we have a conversation in mind. So Alice has some information, Bob has some information, and we have this protocol which Alice sends some symbol over and Bob responds, Alice sends some symbol, Bob responds, and so on and so forth. N symbols. And we can always make these symbols, you know, binary, everything we can express in binary. And we can also assume that basically, more or less without a loss of generality in here, that we go alternating, right? So if I want to send 10 things, well, I send one thing, I let you say something, you just say nothing. You send me a 0, I send the next thing, and so on. So we just go alternating. So I have an n symbol conversation. Now what happens if there's noise? Right, some delta, 10% get corrupted. So the big question is, can we make the conversation slightly longer? Instead of going back and forth n times, can we go back and forth alpha n times for some constant alpha, for some constant size alphabet, and still achieve? And basically, at the end, no matter where these 10% of errors happen, we want that both parties know exactly what the outcome in the noiseless setting would have been. Okay, so a priori, it's not clear that this is even possible. Just using error correcting codes doesn't work, just like Arno told us last time. Basically, just one message being completely corrupted, which is a very, very small error fraction. It's like a 1 over n error fraction will destroy the whole protocol. But what we've seen last time is that there are indeed protocols which achieve something non-trivial. Right? So what are the important parameters that we are looking for here? I mean, what are the important parameters for error correcting codes? Well, one thing is the rate. Right? If I give you a certain error fraction, I want to know by how much do I have to blow up my conversation. And ideally, we want at least constant rate. I mean, maybe we want also a good constant here, but let's for today we stick for just any constant. You know, all the information zeros. I'm sorry. Tomorrow we will actually talk about what that constant is and how we get something reasonable here. For now, we are just happy with any constant. So what this is just 1 over the blow up in length, and also if you use a large alphabet, then you know log of the alphabet size. The other thing that's really important about error correcting codes is computational efficiency, right? I mean, Shannon showed that there exist error correcting codes with good properties. That's a really cool mathematical statement, but it's not really practically useful if decoding and encoding takes exponential time. Nobody uses random codes. They're horrible, right? I mean, they're not useful. So what we also want, we want something that's computationally efficient in decoding and encoding. And then the next question we can ask maybe, what's the maximum amount of errors that we can tolerate? Or if we talk about rate, kind of up to what error rate can we at least get some constant rate? If we at least don't know exactly how the trade-off between error rate and rate is, communication rate is, maybe we can at least determine what's the maximum amount of noise that we can tolerate. Okay? So in the interactive setting, so in the error correcting setting, we know what this is. We get almost linear time decoding and encoding error correcting codes with optimal rate distance trade-offs, more or less. And we can tolerate errors up to, I guess, 1/2 if we go over large alphabet. Right? How does this work for interactive coding? Schulman showed that for some error rate, for any error rate smaller than 1/240, we can achieve constant rate using tree codes, which unfortunately we don't know how to construct or decode, so exponential time, but still. Great result, right? And then, so we haven't seen this, but what we have seen yesterday is actually, if we use also tree codes, but a slightly better protocol, we can get tolerate any error rate of 1/4, that's below 1/4. Right? That's what Anum showed us, this constant rate. Two other prior works that are important. So all of these things are not efficient.
Are they proven to not be efficient, or?
We don't know how to make them efficient.
But it's not a lack of a tree code, right? I mean, because if there's a randomized construction that probably gives a tree code. It's the decoding process.
We also don't have something that, so even, it's both.
Error.
Yeah, so the thing is, even if we have, there's this conjectured explicit tree code, right, which Anum talked about very briefly yesterday. Even if we know that this conjecture is true, even if we know that this tree code exists and we can kind of compute each thing efficiently, we would still get exponential time here because of decoding and encoding.
But Schulman also has this like convolution-based probabilistic construction that's for most choices is a good tree code.
The encoding is efficient. It's
Yeah.
the decoding is not efficient.
The decoding is still exponential time.
Can I ask you a general question?
Yeah, absolutely.
So in classical, in one-way encoding, there was the Hamming approach and the Shannon approach.
Yeah, so we talk only about Hamming right now.
Exactly. So I'm asking, does anyone look into the Shannon version where you're assuming a random model of?
Yeah. So I mean, it's random errors are obviously easier than adversarial errors. If you have it for adversarial errors, you can get it for random.
Sure. I mean, so there are certain things that perhaps people looked into it before.
Yeah. So people have. I'm not going. I want to stick with kind of one model. Yeah. I mean, there's. But basically, everything is more or less subsumed by what we know for the adversarial case. And once you know it for adversarial case, you know what you get for the random case.
For random errors, once you can tolerate constant adversarial errors, you can basically boost that up to tolerate much higher random errors. So I think for random errors, Schulman already showed how to tolerate error fraction of 1/4.
1 minus, yeah, anything that's bounded away from 1/2, right?
And I think for the constant size alphabet, you can reach 1/2 for random errors.
I mean, basically, if you have random errors, you can just repeat every symbol 10 times, right? If you have an error rate of 1/2 minus epsilon, now it's an error rate that's really bounded away from the error rate gets much smaller. And then you build a protocol on top of this, right? It will hurt your rate, but it will still stay a constant.
Well, we don't know any efficient construction.
No, for random, we know efficient constructions. And for adversarial, we do know some efficient constructions. So in particular, Braksky-Kalai showed that there's a randomized algorithm that achieves, that runs in n² time. It can tolerate any error rate smaller than 1/16 and has constant rate. So then by just doing a repetition code on top of that, you can also tolerate any random error rates that's bounded away from 1/2, also with constant rate.
Okay, so do we know a deterministic polynomial time construction with?
No, so deterministic is harder, yes. So that's one of the open questions.
Is that also tree codes or something else?
This also uses tree codes, yes, but only on small chunks. I mean, we will see something similar to this later. right? And then we can also get near linear time, like n polylog time, if we're willing to suffer even more in the error rates that we can tolerate. Okay, so that's basically the state of the art, or I mean that was the state of the art, and now we can ask basically two questions. Just looking at this, one question is, well, 1/4, right? That's the best that's the best that's on the board. Is that the best possible? Is 1/4, and Arno yesterday made a really good case that 1/4 should be the natural limit. That's so that's one question. Is 1/4 the optimal error rates that we can tolerate? The other question is, well, I want to show you actually how do we achieve these efficient protocols. And ideally what we also would want is how can we achieve efficiency and maximal errors at the same time. Okay. So that's going to be basically the whole talk today. And it's mostly based on joint work with Mohsen Ghaffari and Madhu Sudan. Okay. Questions up to this point? What's the model? Yes?
So you seem to have a model where the error is measured over both adversaries, and I see that's why you get the 1/4. What if you kind of say, well, the max error for A is this, and the max error for B is this? Do you get a better?
You get different bounds, and Klim will say something about essentially this model on Thursday. Yeah. Other questions? Okay, cool. So let's start with the 1/4 question. Is 1/4 the best that we can tolerate, or is there something better? Okay. So Arno yesterday said, well, so here's the argument that, let's say, yeah, so 1/4 optimal. Mark. So what we know is that for every protocol pi, there exists a protocol pi prime, which is similar in rate, which is similar in the number of rounds that it uses, which simulates pi against anything that's less than 1/4, right? 1/4 minus epsilon. And on the other hand, the claim was that if you look even at a very simple protocol, in particular for pi equals exchange, I will say in a second what that is. So it does not exist pi prime simulating pi against delta equals 1/4. Okay. So what is exchange? Exchange is really the simplest interactive protocol that you can think of. Alice gets a bit, Bob gets a bit, and they just want to know each other's bit. They just want to send each other each bit. Now the claim is that even that's the simplest protocol where at least both parties need to send something. It's the simplest thing that's not just one way, right? Even this simple protocol, the claim is we cannot simulate with anything that's smaller against an error rate that's 4 or more. Okay, and proof was essentially, well, one party talks less than half of the time. So less than half of, so this is big N, the number of total rounds that we're running. So we can corrupt half of its transmission. And, well, that kills any things that you can do, right? We can interpolate between whether you want to send a 1 and you want to send a 0, and that's it. So, case closed. Maybe. Does somebody see what might be at least questionable about this proof?
adversary doesn't know in advance who will speak less.
Exactly, right? So yes, one party will talk less than half of the time. But how does the adversary know in advance which party this is? Right? Well, so one way to go about this is to say, well, let's restrict ourselves to protocols in which both parties declare in advance who's talking at what time. If we have such protocols, then this proof goes through. Right? If we declare up front who's talking at what time, I can easily look who's talking less, who's talking more, and then we're good. So,
To be
yes?
fair, I just want to point out that we didn't write this proof in our paper. We first assumed that we made the assumption that you were talking about, and then we wrote the proof.
We
We assumed that it was known ahead of time which party would speak in each round, and then we wrote this proof.
Yeah. No, I'm not saying that you tweaked. I'm not saying that you tweaked the model to make the proof work. If that's
No,
So-
I mean the way you wrote it's like there was a bug in our proof.
no, there's no bug in the proof, right?
Yeah.
No. No. I mean the only thing that it needs is it holds for exactly the model where we declare in advance who talks at what time, right?
Yeah.
So, and that's a standard model, right? I mean, that's a model that everybody looked at. So the standard model, and so I want to call these things non-adaptive, right? Because in advance, I'm declaring who talks at what time. I'm not adapting to errors. So let's talk about these models. So we have non-adaptive, and obviously, if you have non-adaptive protocols, also there are going to be some adaptive protocols. And as Anum said, non-adaptive was or is the standard model in which all of these questions were studied, right? Non-adaptive just means we have a fixed communication order, and each round we either Alice listens and Bob speaks, or Bob speaks and Alice listens. And then whoever listens receives what is spoken, except when the adversary interferes. And that won't happen too often. Right? That's a standard model. And this is a perfectly good proof for exactly the standard model. Right? So if we say it does not exist a non-adaptive phi prime, which simulates it against 1/4. Okay. Right, but then still, maybe we can come up with a model that is adaptive. And I claim in reality, communications are adaptive. Right, so let's look at what does this lower bound say, right? Suppose that
I'm not clear about the rules of the game. If the adversary flips a coin and decides who he's guessing will speak more than half of the time, so he has 50% chance of succeeding in his task. Is that considered acceptable?
Oh, that's acceptable. No, that's acceptable.
Acceptable from the point of view of Alice and Bob. Say, he can corrupt it 100% of the time. Then
No. I mean, if we want basically that if you have randomized protocols or randomized adversary, we want to be right at least with 1 minus something negligible probability.
Then what's the problem with why?
Well, let's think about it. I'm going to tell you.
But
It's not trivial.
No, I don't understand something.
the players can learn what the adversary's choice was as the protocol runs.
Yeah,
The players can learn information about
Oh,
exactly. Let's think about it, right? So you can just basically flip each bit with probability half, right? That's one way to ruin this whole thing of one player. You focus on one player, and you flip half of its bit. In the beginning, you flip a coin, which player you focus on, and then for each bit, you flip a coin, whether you corrupt it or not. So that makes this transmission completely useless, and you only spend, on average, kind of 1/4 error rate. That's the thing, right? And this is exactly kind of what works for this proof, right? But now let's think about it, how this would work out in reality, right? You pick up the phone, you call your mom, right? And You say something to her. The line is perfectly clear. Your line is perfectly clear because the adversary decided to pick on your mom, right? Your mom is going to say something.
These protocols tend to be quite asymmetric from very long experience.
Yeah, that's very true, for good reason. So the adversary picks on your mom, right? So whatever your mom says, 50% of that gets corrupted. So you can hear that there's noise. You will not mistake it for something that's actually legible, right? But you can't understand what the heck she's saying. Okay, so now it's your turn again. You say something, right? So,
Mom, watch out, you're being attacked.
right? So 50% get corrupted, which means that we have really no clue what was said, but we know that some errors happened, right? So we respond back, and everything is perfectly clear. Alice, does somebody have a mom named Alice? That would be so cool. Okay. Again, right, says something, 50% of the things are corrupted. It's my turn again, I say something, comes through. And this goes on for infinity. That's not what would happen, right? Because if my line is perfectly clear, but my mom's line is totally blocked out, just white noise, why am I talking? I have nothing to say. I can't even, I haven't understand a single thing of what she's saying, right? So naturally what would happen is I would talk less and I would let my mom talk more, which anyway happens all the time, right? But independent of errors. But
You're not listening to me.
exactly. So once I start pulling back and my mom talks more, the adversary cannot null out 50% of what she's talking, because now he's spending more than a quarter of the whole conversation. So eventually, he needs to spend less than 50%. In this point, I will understand what she's saying, and we can continue with our conversation. Right? So this says at least maybe there's a hope that we can beat 1/4. Okay? And yeah, so let me spoil it. Yes, we can. And we can show that the amount of errors that we can tolerate, 2/7. Quick calculation, 2/7 is better than 1/4. That's good. The surprising thing is 2/7 is tight. Okay? And in the beginning that sounds very surprising, but if I had a few more minutes, I don't want to spend too much time on this. I'm sure I could actually convince you that 2/7 is the right bound, and it's a very natural bound. Okay? We can do this offline, anybody who's interested. I will try to give a little bit of a hint why this is the case.
There might be a problem with misunderstanding if this adaptive scheme. I mean, two people can speak at the same time.
Very good. So let's make this formal, right? So I just made some claims, but I haven't specified a model. I haven't said anything formal. So let me just write down what exactly I'm meaning. So yeah, let's first define adaptive protocols. So here, each player gets to choose, each party in each round can choose whether to listen or speak independently, based on the history, based on randomness, if they want to, whatever. And now we need to consider multiple cases, right? Easiest case, if we have listen or speak and listen, we just do the same thing, right? Whoever listens receives what the other person talks, unless the adversary decides to interfere. That can't happen too often. Right, so this case is pretty clear. If both parties speak, well, it's easy what we do, nothing, right? Both parties speak, nobody listens. Perfect. There's nothing to specify, right? The parties just lose a round. Tough luck for them. Right? Speaking at the same time, never good for them, but it might happen. The case where a little bit of thinking and modeling is involved, what if both listen? Okay. Now, what if both listen? Maybe the first thing you would try is, say, hear silence. Okay? That does not work. So if you define that, say, hear silence, you can actually just communicate totally uncorrupted by communicating versus silence and not silence. Okay? So the right thing to do here is say, if both parties listen, what they hear is undetermined. and we want our protocol to work for whatever they hear. Right? So that's the most pessimistic things that we could hope for. If we can design algorithms for this, it's going to be great. Right? And this is the right model in the sense that also it doesn't allow any cheating. And one way to see this is that we can actually prove upper and lower bounds.
And if they both listen, the adversary can simulate
Noise for
noise.
So it's almost the same thing as saying the adversary gets to choose whatever each party hears for free. It doesn't have to pay for it, right? So it's the most pessimistic model. It's more or less the only model that I know that doesn't allow cheating. It also works very nicely. We didn't think about capacity in this sense, but it also works very nicely. So basically, the whole idea is that I give you the opportunity to adaptively decide, but you should not gain from the fact that you miss to coordinate. If you both listen, if you both speak at the same time, you should not gain an advantage from that. That's the model that does this.
There's a more technical question, which is only important if the messages are small. Is there an end of text symbol? How do I know the other guys?
In all of these things, we declare the number of rounds a priori, and we run for a fixed number of rounds, and then the protocol is over.
So how do I know? Do you assume that I know that the message had terminated, right?
No, so you declare in advance.
Now you're talking.
A single round.
Oh, yeah, it's one symbol sent. In each round, we can now both decide to either listen or send a single symbol, and
Each message is a single symbol.
each message is a single symbol. Yeah, just like before. Okay, is the model clear?
So if we both speak, do we know that we both spoke?
No. You didn't listen. You have no idea what the other party did. Also, if both listened, you cannot distinguish whether the other person actually talked to you and this was what you heard, or whether you just heard the background noise. Yes?
Does the adversary has to decide whether he wants to act before they start acting, or?
The adversaries all knows everything, so it can...
Okay, so he knows that they are going to speak at the same time.
He knows that, yeah, so I guess he gets to see whether they speak at the same time and can decide to interfere and do nothing, or listen at the same time and then decide what he gives them. Okay. So, okay, cool. So, yeah, I don't want to write so much, so I'm just gonna change this. So, the claim now is the following: that for every protocol, so two claims. For every protocol, there exists an adaptive pi prime, which simulates pi against any error rate of 2/7, smaller than 2/7. And on the other hand, the same simple protocol, the exchange protocol, I claim no protocol, even adaptive one, adaptive, non-adaptive, no protocol whatsoever, can simulate the exchange protocol with an error rate of exactly 2/7. Okay, so that's a technical statement. So this is the technical model, this is the technical statement. Is the statement clear?
So for this statement, so you described the model, which is like you allow the maximum flexibility. So for upper bounds, this is the most general model for upper bounds. For lower bounds, maybe not.
This is the most pessimistic model, yes. Right? So if you can get an upper bound, then if you can get a protocol, then that's generally nice.
Yes, exactly. But for lower bounds, so the question is if this lower bound works also in some other models.
In other models, so
because this is the most pessimistic model, so it's great for upper bounds, but
yeah.
For lower bounds it's maybe.
So how would you relax it? What kind of relaxations would you make?
So the question is.
No, I understand the question, but which other models do you have in mind?
So there are several other models, but for example, you can ask what happens when they both listen. If it's really adversarial bit, or maybe it's some other thing, or
Yes, the question is what, right? So if it's silence, you can cheat. If it's random, you can cheat. If it's, I mean, basically, more or less, and generally also, if you want to say what is the rate, right? I mean, this thing has the nice property that each round of communication we cannot exchange more than a single bit. If you, for example, allow a silent symbol, now suddenly you work over a trinary alphabet.
if you allow like random bits, would they allow
That also won't work.
then what
That will be too strong.
that will be
Yeah, I mean, this. I mean, we thought long and hard about it. This, I now, after having thought about it, there are a long list of reasons why I really want to say this is the right model. And then also when we looked at capacity, which was something that we didn't have in mind at all when we designed the model, I think this is the right model to prove both upper bounds and matching lower bounds.
So even so this is the right model, like you're saying that it's like a better model than if you allow like a random bit instead of
Yes.
adversarial bit.
Yeah.
Things like this were known in the early days of distributed computing, that if you allow silence for free, then it allows you really what you call to cheat. You can really...
Yeah, if you allow silence, but if you don't allow silence, if in case it's silence, it's a random bit or something like that.
I mean, you can, yeah, I mean, this is a model. I think it's pretty clear that it's a nice model. We can talk about why it's the best model or to talk about different models. But yeah, so at least this is a very natural formal model for which we can prove things from both sides. Okay. Okay, so I can't really, so actually in the end, you will see how we actually achieve this part, at least more or less. It's not as easy to see why this is the optimal protocol. At least to give you a little bit of a hint of where this 2/7 might creep up and how these things look, I will give you at least a protocol that computes exchange when the error rate is smaller than 2/7. Okay, and that already captures at least a little bit, and then we can talk offline if you want to know more. Okay, so here's a protocol that computes the exchange, that simulates the exchange protocol in an adaptive manner with an error rate of 2/7 minus epsilon. Right? So the protocol is very simple. We run in, for example, 700 rounds. And I allow slightly less than 200 errors, right? 2/7. So I allow 199 errors. The protocol looks like this. For 300 rounds, Alice is going to send her bit. Then for 300 rounds, Bob is going to send his bit. At this stage, both of them will try to figure out if they already know what the other party sent, what the other party's bit is. When do I know for sure what the other party's bit is?
Something like 400 times or something? 60 or
No, so I received 300 bits.
Oh, 300, sorry.
But I know that at most 199 errors. So that if out of these, somebody.
There are 200 bits which are the same, and
then I know exactly. So if a party receives 200 bits which are the same, then these cannot be wrong, and they know for sure that the other party has the bits that they received 200 times. Right? In this case, at this point, they can already decode. Given that they can decode here, so there's going to be 100 rounds here, which we're basically going to decide adaptively on. In these 100 rounds, if you could decode in the beginning, you don't need to listen anymore, right? So you already know everything that you need to know. So in this round, if you can safely decode, you will send. On the other hand, if after this first round you cannot safely decode, well, then you better listen some more. Now, 199 errors. So if one of them receives 200 of the same thing, he can safely decode. I claim with 199 errors, at least one party will safely decode. Why? In order for one party not to safely decode, the adversary needs to spend at least 101 errors on him. He cannot spend 101 errors on both parties. It doesn't have enough. So one of the parties will safely decode. Either both of them safely decode. They will both talk at the end. Nobody will listen. It doesn't matter. They already safely decoded. Otherwise, one party safely decodes. That party will speak. The other party will listen. In total, the other party will have received 400 times and listened 400 times. At most, 199 out of those 400 times are corrupted. So if you just go with the majority, you're good. Questions? Now this is the optimal protocol. To see that really this is the optimal protocol, it's a little bit more complicated, and I won't tell you now why, but at least you got a spirit of the whole thing. Okay, cool. So let's. Yes.
If you had 200 errors validated, how would you break it?
200 errors, it would just put 100 here.
Lost that. You fooled the majority.
Yeah, exactly.
Yeah, so it will break it in, it will just put, basically it will put, no, it will put all errors on one side, right? One party listens at most 400 times. 200 out of those will be corrupted. You don't know which 200 ones. Yeah, so this is the one is the epsilon, right? So with 2 over 7, this with exactly 207 with 200 errors, this should break, and it will break.
Suppose you start with a protocol that doesn't have adaptively chosen speaking order, and you want to simulate it in a way that's robust against almost 2/7 error. Now
so the original protocol, there's no noise in the original protocol, right? We're in a noiseless setting. So there's never a reason for you to speak at the same time in the noiseless setting.
Sure.
So without loss of generality, the original protocol is, there's no non-adaptive, adaptive.
My question is for the general case. So in this particular case, you only needed sort of one round of adaptively changing the schedule of speaking.
Yeah, I mean 100 rounds. But I mean these are blocks of 100.
What you needed to say, oh, here's
Yes.
the schedule.
Yeah. Yeah.
So in general, how many times do you need to sort of...
Also in general, it's 1. Yeah. So we'll see the protocols that actually, I mean, I can give you the description of the 2 over 7 protocol. Hopefully. Okay, cool. So let's switch topics. So this is roughly what I had to say about 1/4. So yes, 1/4 is the best error rates that one can achieve for the standard model, which is non-adaptive. But if you go to, very natural adaptive model, you can beat 1/4. You can achieve 2 over 7. 2 over 7 is tight. Okay. Now we know what the maximum error rate is. So 2 things that I want to still tell you is how to achieve things efficiently, computational efficiency, and ideally we also want to achieve things computationally efficient and having the optimal error rate. Right? So in contrast to the things that are on the board right now, we want the best thing here and the best thing here. Okay. And turns out the only way I know how to do things, and this is a key concept in both achieving 2 over 7 and in getting things in getting things computationally efficient while preserving optimal error rate, is to go over list decoding. Okay, so good fraction of you probably will know what list decoding is from error correcting codes. It's kind of a funny concept, at least in the beginning. If you see it for the first time, you will probably oh gosh. You'll maybe think it's a kind of it's a neat little problem variation of little use. You couldn't be more wrong. So here, list decoding for error correcting code is just the following. Usually I say Alice wants to know exactly, Bob wants to know exactly what Alice said. Right? Now list decoding says that you don't need to uniquely decode what Alice sent. It's good enough to generate a list of a constant number of things, let's say 100 different strings, and one of them needs to be correct. Right? And in error-correcting codes, we know that the distances that you can achieve with list decoding versus the distances that you can achieve with unique decoding is roughly a factor of 2 apart. Right? And the same will happen here. So if we can tolerate in a standard model 1/4 with unique decoding, we will be able to tolerate 1/2 with list decoding. And this will be the key to everything that follows. So Alice, Bob, compute a list of size constant containing the correct outcome. And if you think of this binary tree in the end, basically each outcome corresponds to a leaf. So I'm just going to output kind of constant number of leaves. One of them should be the correct one. Is the definition of list decoding clear? Okay. Now, let me try to give you at least... So why do we care about list decoding, right? I mean, what does list decoding have to do with unique decoding, which arguably we might care more about? Let me try to give you at least one simple example where a problem that's purely about unique decoding really has list decoding hidden in it. Okay, so let's look at at a setting. Let's call it one-way, one-sided unique decoding. We only want one pre-announced party to decode uniquely. Right, so we have Alice, we have Bob, so you go back and forth. There's going to be a bunch of errors in here. And in the end, we want Alice to know exactly what the original outcome was. And Bob might not. It could be 1, could be 2, the outcome could be 3, 4, who knows, right? Okay. So this is a question purely about unique decoding. I think it's also an interesting question. So where's this an interesting question? Think of, for example, as A is a program, B is a database. A is going to make adaptive queries to the database, and the query is going to come back with some noise. In the end, what we really want to guarantee is that the program ran correctly. Right? The program should figure out what the original thing was without noise. Does the database need to know what question we originally asked? No, not really. We don't care. Right? Or your student comes to you and wants to solve a problem, and you're this big database who knows everything. So the student is going to ask you a question: is this true? Is that true? Is this true? Is that true? You could give him answers. So the only thing that's important, you might misunderstand each other on the way. So the only thing that's important is that the student in the end has all the right answers. Do you need to know what he proved? Not really, right? That's okay, right? So this is purely about unique decoding. I claim that if Alice can uniquely decode, intuitively Bob better be able to list decode. Why is this the case? Well, if Bob, in the end, has no clue what Alice wanted to compute, Bob is a huge database. It can only give very limited answers. If in the very end he has no clue what Alice really was aiming at, how could he possibly given the right answers? Right? If there are too many options here, then he could have not possibly given the answers. So even though we're really just asking about unique decoding of Alice, I claim that what we really need to solve in between, at the very least, is Bob should be able to, in the end, figure out at least a reasonably small list of things that Alice wanted to compute. Otherwise, he cannot give the right answers. And so the way all of these things are going to work in the end, we're going to start. So this is the overall game plan. We're going to start with an inefficient list decoder. We're going to have one step which boosts the computational efficiency of this list decoder. Efficient list decoder. Let's call this boosting. Different from the machine learning boosting, just computational efficiency. And once you have an efficient list decoder, we're going to have basically one reduction or a bunch of very similar reductions, which given a list decoder allow us to actually construct unique decoders. Okay. So these are reductions to unique decoding. How am I doing on time? 9. So when do I have to stop? 10:45. So I have like half an hour-ish. Okay, cool. Right. So so the only way how I know to achieve one force efficiently or 2/7 efficiently is to go this route. Start with a list decoder, boost its efficiency, and then reduce it to unique decoding. Okay. So I will try to, in the last 30 minutes, give you kind of a flavor or almost complete descriptions of these two things. Let's see if we make it in time. Okay. Let's start with boosting. Okay. So the boosting is the part which introduces efficiency. So boosting, what we want is we have a list decoder that tolerates some delta fraction of errors. It's not necessarily efficient, or let's actually say we only need it for, the whole idea is to only run the list decoder on very small protocols and then assemble it, many of these executions, to a bigger protocol. Because we only need to run it on a small protocol, even if we brute force over these smaller things, it's going to be much more efficient. Right? And we furthermore going to recurse this whole thing, so we can, instead of actually brute forcing over the smaller thing, we can just reduce it to something even smaller until we get constant size or just logarithmic size and we brute force. Okay? So what we want is, suppose that I have a list decoder that runs for, I don't know, log squared, some constant times log squared many rounds. I want to get a list decoder which basically achieves more or less the same, tolerates the same error rate, has similar efficiency up to a constant, similar list size up to a constant, but works for an n-round protocol. Clear what we want? Cool. So how are we going to do this? Well, basically, we try to compute this whole thing, so it's a complete fast, in blocks of size log squared, and going to protect each of these things. Right? So we run in n over log squared n times a constant, so over epsilon, many iterations.
Can you get a better pen and also try to...
Yes, I will try. Okay. Much better. So we run in n over log squared n over epsilon many iterations. And in each of these iterations, we want to kind of append, want to search down another log squared n of the correct path. That's the hope. Okay. So in particular, what we do is the following. So in each of these iterations, we run the following protocol. We first look at all prior blocks. So we decode, actually. Decode all prior blocks. And then, based on this decoding, we try to interactively find a good place to continue our conversation. Okay? Find a good starting point. Good starting point. Once we have the starting point, we actually, for log squared and rounds, we're just going to have the conversation. Right? So if you think of this big tree, we have already had some conversation that gives us some guess of where the right path might be. We find a good guess. I will make this more precise in a bit. But once we have the starting point, we will continue for for log squared n blocks, rounds. Okay. And of course, we don't want to do this in the clear. Right? So this in total, this is hopefully going to be quick. So this is only log squared n long. We want to protect this whole thing, and we're going to use the delta list decoders that we assume that we have, and protect this whole thing here with a delta list decoder. And then we're going to iterate this, this often. So we again run the next block in which we decode, find a good point, find starting point, continue the conversation, and so on. Right? And we do this in over epsilon log squared n off. Okay. Now, the parts that we kind of need to be make more precise is this part, right? I mean, what do I mean with decode? I mean, decoding is actually pretty clear, but once we have decoded, how do we find a good starting point, right? So these are list decoders, right? So at some point down here, I can look at what happened in these conversations, and I can decode them, right? What will happen when I decode them? Each of the parties will generate a list of possible outcomes. What is an outcome here? An outcome is a starting point and a continuation of the path. So we get, for each of these things here, we get a constant number, let's say 100 combinations of starting point and continuation, starting point and continuation, 100 of those. Right? And there's going to be like order n, roughly order n many of those. If you're deep down there, we have all of these things. Now, one of these continuations and one of these starting points is the correct one if the error in this block was smaller than delta. If the error was larger than delta, we have no guarantee whatsoever. Everything could be completely made up. Right? So basically, if we decode all of the blocks that we have before, and we write down the starting points, continuations, and we just look at what were the edges, what were my edges, which were used in these paths. These are good candidates for useful edges, right? Hopefully some of these blocks were actually correct, then the useful edges are among this set. So what the parties are going to do is they look at all the edges involved in all these paths, right? So it gives us, so take all edges. So Alice takes all A edges. Getting small, I'm sorry. Takes all the edges and of the prior blocks, and I claim that this forms a tree. Right? And the size of this tree is at most linear, really. Yes?
So can you draw a protocol tree?
Yes, that's right. So our protocol generally looks something like this. Now, Alice, let's try to use some different colors. So Alice knows the answer to the first question. Right? So this one was this. Alice knows.
I think I understand the big plan that you laid out. So list decoding will give you a small set of leaves.
Not of leaves, right? It will give you, every time it gives you a starting point and a log squared and long path that continues towards. Mm-hmm.
And how do you propose to repeatedly use list decoding on this tree?
So each
round or each set block. Yeah,
each block will give you 100 starting points, which are somewhere in the tree, and a path from this point onwards, which is log squared and long. Look at all of the edges, all of your edges, which are on this path, for all paths and all times. So this is a random set of edges. It's a subset of your edges, and right. So you take that set of edges, and hopefully a bunch of good edges, which are actually on the correct path, are among them.
No, so very first application of this block?
Oh, first application, finding there's nothing to decode. The good starting point is the beginning, is the root. It's just the very root, and you just run the first log and rounds.
And then you will get certain number of nodes at...
Yeah, so you get a bunch of number of paths. You include all of the edges. How many of those edges are there? 100 times log squared. Now, given these edges form a tree, right? I mean, basically they're just like simple passes from the root. Now you take this tree and you find both of the parties have a tree, and they try to find a good starting point. I haven't told you how they find a good starting point, but basically both parties, when they decode, they get a tree. It's a tree of polynomial size consisting only of their edges. And the good thing is, if they take the intersection of these three, there's only one path. And we want to find the deepest leaf on this path. So the problems that we're trying to do here is something like tree intersection. It's a promise problem. I give you a bunch of edges. I give you a bunch of edges. The intersection of them has exactly one unique path. Find it, and find it quickly. Right? Yeah, so if we decode, we get a tree. And finding a good starting point is really doing tree intersection. Does that make sense so far? So if we can solve tree intersection in, let's say, log squared n rounds, we would be very happy.
But could you repeat what happens in the next round? So, okay, I understand the first round.
First round, we just take the root as a starting point. We compute the next log squared n rounds. We protect it by a list decoder. Now, in the next round, we look at the outcome of this list decoder. This basically gives us 100 passes. Both parties get 100 paths, which are consistent with their edges. And in total, you have like 100 log squared n edges. The intersection, the union of these edges, has exactly one unique path, which might be the empty path if this was too much corrupted. It will be the correct path if this was not, if the errors in here were less.
Maybe it was to say that you may get any passes, but if each party has to make consistency for every pass consistent with edges.
Yeah. So the edges that you keep are only your edges. So every edges that you keep are consistent with what you have. Since if you take the union of them, they can only be. It needs to be consistent with you and me. So it's only one path. We want to find the deepest link of this path. This is where we want to continue. Okay. And yeah. So this tree intersection problem is not hard to solve if we want it with high probability in a randomized manner. We just do binary search and hashing. Okay, so how exactly do we do this? Let's generate some log and long independent randomness. Alice sends that one over. Now we have some shared randomness. We use that randomness to hash each of these edges has an up to order n long description. But they're only polynomially many of them. Right? So let's take this order n long description of any edge and hash it into a log n bit string. And because we use a random hash, with high probability that name will be unique among the order n edges that there are. Because it will basically be a random log n bit string. Right? So with high probability, we have a short description, unique description for every edge on your side.
These random bits could have been corrupted.
No, in the sense that this is what's happening inside here. Right? So here we're writing a protocol in which we assume there's no noise, and then we protect this protocol with a list decoder. So here we can assume that there's no noise, and then if the total noise in here was smaller than this, then one of the outcomes will be the correct no noise outcome. Yeah, so essentially we really want to solve this with no noise. So once I have this unique description of the edges, I just do binary search. So in particular, Alice takes her tree. So there's going to be one edge, which if I remove it, the two subtrees, both of them are constant size smaller. Let's test whether this edge is on the path. Well, I send the name over and ask Bob, hey, do you have an edge that matches this description? Do you have this edge? If he also has this edge, then it's on the path. If it's on the path, we only need to search in the subtree. Right? We discarded everything that was not in the subtree, which was at least some constant fraction. On the other hand, if it's not on his path, I don't need to search in the subtree. So Alice discards the whole subtree. So with one exchange of log n of a log n bit identifier, she cuts down her tree by half. She does this logarithmically often for a total communication of log squared. And we have found the deepest point in the tree with high probability. Now, the searching part is log squared long. This is log squared long. So in total, this is still only log squared long, and we can protect it by the list decoder. So this is a protocol. I guess the only thing that I need to say, how do we decode in the end? What do we output? Right? What we output is, in the end, we decode all these lists. So this gives us, again, a tree of at least, of at most polynomial size, like n over epsilon many edges. Any leaves of that tree, I will output.
Can you repeat what the hashes are for the tree intersection problem?
What the hashes are. So basically, I just take a random hash function. So the property for the hash function I want is that if I have polynomially many things, like order n many edges, which have a long description, I use the same random string to hash those, the same seed to hash those into like log and bit identifiers. And what I want is, if they are different edges and with high probability, they will have different names.
Okay, so one way to view it is the hash just makes it like a protocol with a much smaller tree, and then you just do the naive protocol on this tree.
On a much smaller tree.
You're relating the edges so that you just get a small tree.
Yeah, the description of the edges is small now. Instead of kind of describing an edge by the whole path to it, right, which can be order n long, I want to give it a short nickname, right, such that you and I know which edge we are talking about.
I mean, so you can view the entire problem that you're trying to solve here as tree intersection, right, on a big universe. The entire communication problem is a tree intersection problem.
Yeah, so we just want this promise problem.
A space to a smaller space, and then somehow solving it using hashing. That's what the list decoding is. So that is an accurate description of
to a smaller. So I'm not sure what you mean with you reduce it to a smaller tree.
So like if you start, before the parties start communicating, they all have their sets of edges.
Right.
And they're trying to compute the tree intersection problem.
Yes. Right. And now we have trees that are smaller, and we can do this efficiently. Yeah. So let's try to finish this up. So why is this? Why is this kind of quick intuition? Why is this correct? So definitely it's fast, right? Why is it correct? Two things we need to prove. The correct path will be included in the list. Right? Why is this the case? Well, in order for a block to get corrupted, to not make log and progress on the correct path, log squared progress on the correct path, there needs to be at least a delta fraction of errors. But the total error rate is an epsilon smaller. So at least kind of an epsilon fraction of everything here will go through, have less than delta fraction of errors. Right? Since we're running for an epsilon number of times more often, it really means that in this epsilon fraction of times, we will be able to go all the way to the leaf. Why don't we output too many things? Well, essentially, the number of edges that we have is still, linear, n over epsilon. And if you output all the leaves that kind of go deep enough, there can't be too many leaves that we output. And so the list size will still be a constant. It will be 1 over epsilon factor larger, but who cares? It's still a constant.
Once again, why can't we use large? Why can't be very large out list?
So the total number of edges is small, right? The total number of edges in all the lists is at most kind of 100 times n over epsilon.
Yeah, but you can't have a lot of leaves in a tree with n over.
Yeah, so you're going to take the original protocol and just on every leaf append kind of a little bit of a path. And then you only look at leaves that kind of follows this path. Now you can only have a constant number of, now you can only have, constant number of leaves. Okay. Okay, yeah, so I still want to give you a little bit of a hint how we do the second part, how we do this reduction. So unless, is the intuition clear? Is the protocol roughly clear? Yeah, I think so. Cool. Okay, so last little part. If you have an efficient list decoder, how do we get a unique decoder? Okay, and essentially, so what are the formal statements? Formal statements is if we have 1/4 minus epsilon list decoder, then we get a 1/4 minus 2 epsilon unique decoder. That's the first thing, and what's interesting about it is that we really don't even need an optimal list decoder to get this. Right, so optimal list decoder would tolerate 1/2. Here even a list decoder with 1/4 is good enough, and essentially we get list unique decoding for free, non-adaptive, right? The other things, basically the same reduction, just the proof is a little bit more complicated. If we get a 1/2 an optimal list decoder, 1 minus epsilon list decoder, then we can also get a 2/7 minus 2 epsilon adaptive unique decoder. And we can, for example, also get a 1/3 minus 2 epsilon one-sided unique decoder. 1/3 is also the optimal error rate here. Okay, so basic, and these are black box reduction. I just need to know that there exists this list decoder, and if it's efficient, then also this reduction will be efficient. Cool. So how does this reduction work? So let's focus on this case. Right? How do I, if I have a 1/4 list decoder, how can I actually sort out the right list? So maybe the first thing that one could try is, well, let's first run the list decoder. This gives Bob a list and Alice a list and Bob a different list. And if the error rate here is smaller than 1/4, then the correct thing is among it. Now, if you have these lists, again, this is only kind of a linear number of edges. The correct ones are hopefully among it. So if I just take those edges and send them over using an error correcting code, that would be great. Right? So use an error correcting code. Alice looks at all the A edges in L and sends those over to Bob. And Bob takes an error correcting takes all the B edges in L prime, wraps them into an error correcting code, and sends those over. Okay. If the error rate here was smaller than 1/4, these lists include the correct edges. If these error correcting codes can have a distance of 1/2, if the error rate in here is also smaller than 1/4, then these error correcting codes will be at most 1/2 corrupted. And these error correct, I can decode these A edges and these B edges. Now, if I can do this, then I just intersect them with my thing and I get the correct pass. Right? So this attempt will work if the error rate in here is at most 1/4 and the error rate of here is at most 1/4. And we first do list decoding and then we pick out the right thing by using error correcting codes. Why does this not quite work yet?
Can you put all the errors on the...
Yeah. So the adversary can, like this makes up half of the protocol, this makes up half of the protocol. So there's no guarantee that the adversary nicely distributes the errors 1/4 here, 1/4 here, right? It might decide to completely kill only the first parts, and it can corrupt this with 1/2, and it can kill this, or it can corrupt this with 1/2 and kill one of these error correcting codes, for example, completely. Right? So we still want to kind of do this, but ideally we would like to run them at the same time. The problem with running them at the same time is we can't really send the error correcting codes if we don't have these lists yet. Okay? So we kind of, so how do we get around this? Find a protocol looks almost like this, just we repeat it a bunch of times. So in the beginning, we run the list decoder, and we get a list 1 and a list 1 prime for Bob. Okay? Then we run this list decoder again. Same list decoder, we get an L2 and an L2 prime. But now, in addition to running this list decoder, at the same time, I will also send error correcting codes for A edges of L1. L1 and B edges of L2, L1 prime. Of L1 prime, right? At this point I have them, I send them over. I repeat this a bunch of times, 1 over epsilon, so this is n rounds, and in total I run this kind of 1 over epsilon often. Okay. And so this just writes a third round. We again run a list decoder, we get a third list, 2 lists on each side, and now we don't just send L1, but we send all the edges that are in L1 or L2.
And these error correcting codes are inside the list decoder?
No, these basically we use a large alphabet. On one part of the alphabet, we run the list decoder, and then we append kind of I mean, this is a number of n symbols, right? The length of this is kind of one string, constant number of strings of length n. We might put this into an error correcting code, which is like order n symbols, and we just kind of send a symbol that corresponds to the list decoder, and we, cross product it with the symbol of, we just send tuples. Right, so that's kind of how we run them at the same time. It will blow up our alphabet by double our alphabet, double the bit size of our alphabet, but for now we don't care. So here we send the A edges of L1 and L2. Okay. Now, in order for the adversary to, so how do we decode in the end? We only look at the error correcting codes. We look at what passes, what edge sets do we get. Each of these error correcting codes, we decode to the closest code word. It corresponds to some edge set of the other party. We look intersected with our set, what endpoint does it correspond to? And we essentially take some kind of majority. So we do soft decoding. If you're something that's very far away from something, we assign it very little confidence. If it's exactly kind of points, and you assign it a lot of confidence. But you just kind of look at the overall confidence, and you pick out the one pass that has the highest confidence. Now, for the adversary to kill this, it needs to corrupt the list decoders. So once it doesn't corrupt one of these blocks sufficiently enough, from there on, the right edges will be included in all the error correcting codes thereafter. So essentially, for the adversary to kill this, it needs to kill all the all the list decoders up to some point. So for one round, it's good because we didn't have a chance to transfer it over. But except for this one round, it needs to kill all the error correcting codes thereafter. Otherwise, we get the right thing over. That's the intuition. And then you just do the math. And all these, so this is how this works. And all these things here work essentially the same thing. So instead of having kind of this list decoding part, we basically, for the 2 over 7, we have a protocol that roughly runs, we run this for three 1 over epsilon mini rounds. 6 mono epsilon mini rounds, and then we have kind of one round in which one party should be able to decode and just sends error correcting codes. Right? List decoding works the same way. Kind of we mirror what we do for the exchange protocol, and we put in these list decoding things, and that's a reduction. And then proving that it works is a little bit more tricky, but I think the intuition should be clear. Now, I haven't shown you how to actually get a list decoder with 1/2, right? So that's a big piece that's missing. So Klim is going to talk about that on Thursday. One interesting thing to note is that if we want to get, for example, 2/7, we need Klim's result, right? What we're going to do, we take Klim's result, we boost it in efficiency, and then we run this reduction, where we need a really good list decoder. Interesting, for the 1/4 result, you already know how to do it. Why? We have an inefficient list decoder with error rate 1/4, namely what Anup gave us. It's a really good list decoder. It has list size 1. It's still a list decoder, right? So it interprets Braverman-Rao as an inefficient list decoder, boosts its efficiency using the tree intersection part, and then applies this reduction, and you get a 1/4 unique decoder, which is computationally efficient. Okay. Let me finish up with kind of some open questions. So one good open question is deterministic protocols. So all of these protocols are efficient, but they're randomized. Can we get something that's efficient and deterministic? Interestingly, actually, these protocols are non-uniform. You can make them non-uniform deterministic. So instead of kind of making it r time n squared, you can make it d times n squared / poly. So that's halfway there.
The tree code could be...
No, because even if I give you a tree code, how are you going to decode it? So even, here, these are really exponential times. This is not p/poly. So here we get something that's, so if I think really hard, if I run my supercomputer, it can compute a really short circuit which computes what I want, which is deterministic. I still need to really search very hard to find it, but then the circuit will be small. Right? That's not true for anything that we know how to do with tree codes. So uniform deterministic, we don't know how to do. All of this assumes that we operate over large symbols. What if we want binary protocols? It's everything that you can do here. You can do, let's say, binary protocols with a loss of a factor of 2. Just using error correcting codes is really easy. So we can, for example, get a 1/8 unique decoder for the standard model. The question is that optimal? And we don't know. We can prove that you can't do better than 1/6, but where between 1/6 and 1/8 the right answer lies, I don't know. The proof that works, kind of the error correcting proof, for the lower bound doesn't hold because we have feedback. That's another big question. Then, well, the obvious other big question is rate, but we're going to talk about this tomorrow. And I think that's basically it. Questions? I'm sorry, in the end, obviously, it went a little bit faster.
Questions?